So a function is concave up if the second derivative is greater than 0, and it's concave down if the second derivative is less than 0. So to find out where this is concave up or concave down, we could find the second derivative. So let's start with the first derivative, the power rule. And then here's the second derivative. And then if we want to know where it's concave up and concave down, we can set this equal to 0. This is like a straight line, right? You don't even have to really solve from here if you are good with y equals mx plus b. But this is a straight line. The y-intercept is -8. The slope is 6. So it's going to be concave up when it's positive, concave down when it's negative, because this is a graph of the second derivative. So if you set that equal to 0, and you solve, add 8 to both sides, divide both sides by 6, you get x is 4/3. So that's where it switches. That's where it crosses the x-axis. So this thing is concave up when it's positive. So from that graph we sketched, that's 4/3 to infinity. And then it's concave down from negative infinity to 4/3. Okay. So part B says determine the locations of inflection points. Inflection points are where it changes concavity from being concave up to concave down. So that's what we did when we set the second derivative equal to 0 and solved. Okay, we found this is a potential inflection point. We just need to make sure we went from being concave down to concave up at 4/3. And that's definitely what happened. So 4/3 is our inflection point.